I think it's the MOC lab. Y'all go ahead and turn into that right now. Get out your lab book. Huh? And them, huh?
It's 3-phase motor.
What?
No.
No, your lab book. Your lab book.
He said turn the MOC in your lab.
In your lab book. I got it over here.
No, I'm saying he wants to see the lab. I just turned it in.
Oh, well then it's not up there then.
No, I turned it in.
I know, well it's not up there then. I've already got all the to be graded labs. Oh, just now? Yeah, go get it. I'm sorry. I thought you turned it in last class. So, and I don't know what happened when they reprinted this thing. Yeah, MOC.
You want the nameplate lab turned in or you want the
Yeah, I want the nameplate lab turned in, but I want y'all to turn to MOC. Not the nameplate, the MOC too, I think. Isn't that the one where you wire the motor up to? Oh, yeah.
Yeah, that's what you want. Oh, you want experiment 2.
Yeah, 2. I'm sorry. Yeah. Sorry, I confused y'all. I want MOC 2. And this is where y'all going to connect a motor up. A 3-phase motor. And y'all looked at the nameplate. The nameplate that y'all looked at is exactly, it's the nameplate off that motor right there. So it's a 3-phase motor, right? Can run on 208 or was it 220 or 460. And then we looked at the full load current. We know it runs at what, 1725 revolutions per minute. If it's running under the right voltage and the right frequency, right? You'll understand that. And the right connection. And then we didn't give you this part, but this is in the lab book. Is how to show you how to connect this thing for high voltage or low voltage. Now, of course, we're going to connect ours for low voltage. And if you look at yours, and you look at low voltage, and you look at high voltage, what do you notice? They are the same. Could that possibly be correct? Huh? No. So if you look at the lab book, it's going to tell you to do it according to the nameplate on the motor. And I could show you my book, the one that's got corrections in it, and mine's right. So I don't know what happened between publications. But so use the nameplate on the motor. But what we do connect the motor in series. For low voltage, we hook them in parallel, right? And for high voltage, we hook the coils in series. Now on our motor, they're not labeled 1, 2, 3, 4, 5, 6, 7, 8, 9. They're labeled T1, T2, T3, T4, T5, T6, T7, T8, T9. And these are terminal numbers. So according to this, and you've got all the terminals coming out, you got 2 additional ones, guys. This guy has got an electric brake on it that we never use. Never use. But we could. Now that's why the motor is so big, because of the brake mechanism on the back. And I forgot to bring up my phone. Yeah. So here's the actual nameplate on the motor. Of course, this says that this is for low voltage, and it says this is the way we connect for high voltage. Everybody okay? So what it says is, when I look at my terminals, so here's our terminals, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is brake. What I want you to do before you use this thing is I want you to attempt to spin this the shaft with your hand. If you can't spin it, don't put power on this thing. The manual control of the brake is back here on the back, and you should be able to turn it, and it should lock down, and now the motor should spin freely. So, of course, the problem with men is they see a knob, they don't do what? They don't turn it. So that's why you need to do it. If you don't, you're going to kick the overload. It's not going to hurt the motor. It's just that, well, yeah, here, what'll happen now is it might blow the fuses. Well, I doubt it will because there's 10-ounce fuses in there. But you could burn the motor up, right? Because we're not using overloads protection. So what's the first thing I was going to do? Just come over here and just, if you can't spin it real easy, you're going to do what? Just turn it. It looks like it's counterclockwise. No, clockwise. And then that releases the brake and it should spin pretty easy. So we're not going to use these two terminals right here. This is the way we can electrically engage the brake. So here's our 9-lead motor. 1, 2, 3, 4, 5, 6, 7, 8, and 9. These guys right here. And this terminal board is there now. Yeah, just kind of now normally all this would be inside this panel, so the manufacturer's numbers would be in here. We would pull these out, and there would be either terminals in there that I could hook wires up to, or it'd have to be a bunch of wires, and they usually have metal rings on them with the numbers on them. But there's a procedure in your textbook, guys, that if you run into a 9-lead motor and the leads, and the problem is people, if it's got those metal tabs out on the end, guess what they do sometimes? They cut the dang things off to make them short. And then after that, you're messed up. They wire them because what they happen is they cut them off and strip them and wire them at that instant. But you come in there and you got a problem and there's no leads on there at all. Right?
You want to know what number?
Yeah, well, what you would probably need to do is just kind of mark them before you, but there's a procedure, guys, that you can go through on the book that actually tells you. You can find the windings. You can find windings that are connected together with an ohm meter. So that's what you start out first, is connecting with find the ones that's connected with the ohm meter. And then you'll hook them up and you'll measure voltage, and if it feeds back through, it'll be lower. So it's a procedure. It's really good in the textbook. Now this one that we got, that I got, it's right. So don't use, you might need to make right now. It says, use the nameplate on the motor. Don't use those, the connections that they show you in the textbook. I mean, in your lab book. Because when you look at them, they're the same. But when I look at the motor, they're different, right? You'll see that. They're okay? So according to this, if I'm going to wire it for low voltage, it says I need to put a jumper between what? 4, 5, and 6. So just use some of your little short jumpers and jump 4, 5, and 6. Okay. Then it says I need to do what? I need to put a jumper between terminal 1 and 7. I need to put a jumper between terminal 2 and 8. And I need to put a jumper between terminal 3 and terminal 9. You understand that? Okay. And then you're going to come up here on your disconnect. Up here, you got L1, L2, L3, and you're going to bring that down into L1, L2, L3 on the, to T1, T2, and T3 on the motor. So T1, T2, and T3 will have two banana plug jumpers in it, right? I mean, banana plug terminals in there. Are you okay? Any questions on that? So this is pretty simple. So that's all there is to wiring it up. So this is the this is the circuit you're going to wire up. All this you don't have to wire up. This is inside the disconnect. It's inside the disconnect. And then you're going to have a, what does it say? T1, T2, T3. And then you'll just bring T1 and hook it up to T1 on the motor, T2, and T3 on the motor. And then you're gonna get me to come over there. You're gonna, I'm gonna put power on the thing. As soon as I pull it out, the motor's gonna take off and run, right? I understand that. And then it's gonna have you measure some voltages and stuff like that. Then what it's gonna tell you to do, it's gonna tell you to disconnect it, and I think it tells you to swap T1 and T3. But what's gonna happen when you fire it up when you swap T1 and T2, T1 and T3? It should reverse it. So what you need to do is I'm gonna come over there and I'm gonna say, okay, which way is the motor supposed to run? Right? Because if you don't know which way it runs, and this happens all the time in this class, people aren't even paying attention which way it's running, and then they reverse it and they don't know if it reversed because why? They didn't know it was running in the first place. Okay? And that's all we do on a three-phase motor. It's pretty simple to reverse a three-phase motor. Are we okay? Any questions on this one? All right. Huh? Not now. Pretty easy, right? But don't, it says on the lab, if you look at my correction books, it says don't use these, use the nameplate of the motor. It says that, yeah, but look, it says so they made a mistake. But what's so dang funny is I've got an older version of the book and they're right in mine. And that one right there is a reprint. So somebody went in there and changed it. So we got DC motors, we got AC motors, and that's it, right? So how do we reverse? What's the industry standard way of reversing a DC motor? Armature, right? Swap the connection on the armature. We could swap it on the field, but that's dangerous for a shunt motor, a compound motor, because the motors could run away if the reversing circuit fails. Single phase motors. How do we reverse single phase motors? So DC motors, we reverse the connection of the armature, right? Which some people call the rotor, which is not correct for a motor, for a DC motor. So single phase. We got two windings in a single phase motor that we're going to do, that we dealt with. We have what we call shaded pole motors. We have stepping motors and brushless DC motors, but we're not worried about those in this class. We're looking at either split phase motors. So we looked at what? We looked at capacitive motors and we looked at split phase motors. So how do we reverse them? Nobody was paying attention in class. So we got two windings on these motors. What are they called? Huh? What's the two windings called inside a single? Start winding and what do we want the motor to do? We want it to run. So we have two windings on the single phase motor called the start winding and the run winding. Which one do we reverse? Which one do we swap to make it reverse? Start winding. And of course, three-phase motors, we do what? We just swap, yeah. L1 and L2. So we have to come up with some type of circuit that would allow us to swap these. Now, we know what jogging the motor, what's jogging the motor? Run the motor in short burst, right? What's plugging the motor? well, without letting the motor come to a complete stop. So we got to come up with some way that we can prevent from plugging the motor. So technically, when you reversed your ceiling fan, you should turn it off, let it coast to a stop, right? You understand? And then reverse it. But almost nobody does that. You can hear it scream at you, right? It hums real loud because it's pulling a lot of current. So DC motors, we're going to look at a bunch of circuits. We'll just look at the armature circuit. This come up here. One of the most popular ways of reversing a DC motor. So I could do this. So we could come up here and we could have a switch. And up here, I could put like plus 12 volts. Down here, I could put minus 12 volts. And then I could put a switch, and then I could bring it to. So this is the symbol of the armature. We draw a circle, and we put two little things on it like there. That's basically trying to imitate the brushes. And then I could come over here and have a common right there. So right now the motor will be running in one direction, and we flipped it up to the plus 12, then that would make it reverse, right? Everybody understand that? That's what we've done is reverse the current flow through that. Now what's wrong with this circuit? Is there any way to prevent this thing from plugging? No. You're going to flip that switch. What's it going to do? We're going to change direction, right? I understand that. We could add a center off position. We could have a center off position. And then what we could do is we could switch it to here until it did what? Until it stops. And then switch it up. And a lot of the circuits that we do depends on you. It depends on you not plugging the motor. And of course, sometimes you might have to, right? You understand that. We do have what we call an anti-plug-in switch. I'll come over and show you all that. I'll find it. I forgot to get it over there. But most of the reversers depends on the operator to give the motor time to do what? To stop. Another disadvantage of this is I have to have two power supplies. I'd have to have what? Positive power supply and a negative power supply. So what we would like to do, we'd like to come up with, I mean, I've got a car seat in my car, and it doesn't have a negative, my car does not have negative voltage, but yet I can run those motors front and back, right, on your adjustment on your seats. That means we got to come up with some type of circuit where I can reverse those things without plugging them, and of course, with a single power supply. So one of the most popular circuits we use in DC is what they call an H control. See how I got its name? Yeah, and we'll put a common down here, and up here I'm gonna come up here, and I'm gonna put my plus 12 volts. So what we would do is these contacts would be controlled by relays, right? We could have switches. And let's say if this was reverse, and this down here would be reverse, and if this was forward, this would be forward. So that means if whatever's controlling the reverse, which would probably be a relay, if I hit that one, that would close this contact, that would close this contact. So now current would come up, flow this way through the armature, would come up and go that way. See that? And then of course, so let's just leave that one red. Oops. Lost my R. So which way did we go that way? So this way we came through the motor in this direction right here. Now, if we close the reverse circuit, let me make a, I'm gonna make a, so I'll make it blue. And then this one would close, and this would close, and now our current flow would be up, and now it's gonna go through the motor and what? That direction and up through here. So what we would do is somehow we're going to have to come up with, we're not going to switch these at the same time. Because if I had a circuit that went directly from forward to reverse, then that means I would plug the motor, right? So we ought to come up with some type of circuit where we can do this and not give the motor time to stop. So normally what we do to prevent it from plugging is we come up in here, we're going to use 2 relays. And what we'll do is right now we'll just use a common stop button. Y'all giving me some very interesting symbols for buttons, guys. And then I could come over here, and then I could put a button, and we'll call it forward. And then since this is DC, we don't need overloads. And then I'll call this guy forward. And then I'll come in and seal it in. This guy, let's just call it F. I don't have to. And then I could drop down to here, right? And I could come over and put another start button. Call it reverse. We're calling this F, and we're calling this R. By the way, y'all losing a lot of points right here. Y'all drawing y'all circuits. And I told y'all I was going to take off for it. That's not a lot of points, it's 2 points. If you don't have a dot, you don't have a connection. Everybody understand that? So everything I draw, you always see me put my wall. Okay, so what's wrong with this one? So we got one stop button. We got one. There's definitely this. We could have problems with. It's not connected. No, it is. You just can't see it. Just a little bitty dot. All right. So what would happen if some idiot came in here and pushed the forward and the reverse button at the same time? Well, what would happen is I'm going to come over here. So here's my motor circuit. Here's my power circuit, right? And of course, this would happen. Somebody would come over and say, hey, let's see why this works. Okay, so this is forward, this is reverse. I mean, I'm sorry. Good. And this would be forward, and this would be reverse, and this would be reverse. I press one right there. I press that button right there. That would close these 2 contacts. I press that button right there. That would close these 2 contacts. I have a direct line between my negative and positive on my power supply. I just created a short circuit. And somebody would do that, right? So what do y'all think we need to do to prevent this from happening?
Like an override.
What do you mean by an override?
So you won't allow you to put both buttons at the same time?
We could put a, we've got that capabilities. We've got what we call mechanical interlocks that we could put. Well, what we would do is I would come up here, right here, and I'd put a contact right here and normally close, and I would give this to R, and then I'd come on down here and put a normally close right there, and this belongs to L. So I come in here and I press forward, this contact opens, right? You understand? We come over here. So what would happen is, so I hit the forward, it comes in, right? You understand? So here comes the power. Touch it, comes in, flies over there, hits forward, seals itself in, right? You see that? And then, but what's going to happen to this contact? It's going to open up. So now I'm going forward, and the thing's running this direction. Well, I come over here and hit this reverse. Well, that's going to let the power go to right there, but then it's going to stop. It can't get over to the coil, right? You understand? So this is what we call electrical interlocks. So just about every reversing circuit that uses two relays, we're going to put electrical interlocks on it. And that prevents you from doing what? It don't prevent you from pressing the forward and reverse at the same time. And it would be impossible for you to do, but because it would be, one of these guys would come in first, right? You understand? Even if you came over there and none of them was running, you pressed both at the same time. Whichever relay came in first, it would do what? It would kick the other one out. So this is called electrical interlocks. We could also do what this guy does. So normally we like to put multiple interlocks in here in case one fails. So this is a reversing contact right here. And unfortunately, and we have several of these over there on the Amatrol manufacturing line. And what they have here is they have a mechanical interlock. So if this guy right here is energized, I can't do this one won't energize. If I got this one energized, then this armature or plunger right here can't do what? Can't go. So these are mechanical interlocks. So this is a reversing contact. Here you go, Mark. Don't drop that on your foot. So that's what we would prefer. And by the way, what we would do is we would come in here, and if you see this, it's just like on push buttons. We would have a dashed line running between this guy, and then it'll hit a V, and it'll come back and go to that one. If you see that on it, it's got mechanical interlocks. These dashed lines like this means mechanically connected, right? We looked on push buttons. I mean on so you'd have it, but it's going to be in a V better than what I've drawn. And what would this circuit reverse? Well, we're going to see that this basic circuit would reverse every motor that we have. It would reverse a single phase motor. It would reverse a DC motor. It's just how you wire the contacts to the relay. But this is a basic right here, reversing circuit for an electrical motor. It's how I wire the contacts, right? You understand? So on a single phase motor, I would wire them to reverse the start winding. On a DC motor, I would wire them to reverse the armature, right? On a three-phase motor, I would wire them to reverse L1 and L3. So we do have manual reversers. This is what they're showing here. This is actually a motor starter. What makes it a motor starter and not a contact? Got what? Got overload. This is for three-phase, by the way. And these motor starters, or these contactors, that's the way, so normally what we do, this is industry standard, is if we bring power in the top, and then we're going to hook our motor at the bottom of the relay. So all these relays are going to be mounted vertical. So up here on your motor starter on 3-phase, they're going to be labeled L1, L2, and L3. And down at the bottom, it's going to be labeled T1, T2, and T3. That's just the way industry does these contactors. Then I'll show y'all. Are we okay? So this is the way we would reverse a 3-phase motor. A wiring diagram illustrate. This would be a wiring diagram. Okay. These would be controlled by our relays over in our control circuit. So here they got one labeled F and they got one labeled R. F and R, right? Okay. These are the, what's these a symbol for? This is a symbol of a fuse. These are like this, right? These are hooks. And they come in from different directions, right? This is an overload sensor. So that's the sensor that actually senses the overload. And then it controls the contact that's over in the control circuit, right? You understand that? And of course, these are our connections, L1, L2, L3, but it don't show how, so notice when it comes into the motor's labeled T1, T2, T3, and the bottom of our power relay is labeled what? T1, T2, T3. So it's straightforward as long as we're not reversing. But what we got to do is come up with some way to only reverse what? 1 and 3. So what we do is we bring in our 3 lines. Here comes Tennessee Valley Authority. And we bring them here, and we bring them into our contactor, into the ones labeled L1, L2, and L3. And then we put jumpers here. We take these over and go to L1, L2, and L3. So you just jump across the top. You just jump them together, right? Does that make sense so far? So you don't switch L1 and L3 on the top of the relay because that would create a short circuit. We always switch on the output of the relay. That's where we do our switching at. Not on the top, on the what? On the output side. Everybody okay? Lightened up a little bit, didn't it? So we notice on this one, let me change color. So we bring this first one, the one that's on your left, or the one directly above the motor, and you bring this straight through. So we're going to bring L1 to T1. We're going to bring what? L2 to T2, and we're going to bring L3 to T3. Now coming from the other way, here's L1. On the other side, we're going to jump this over to what? T3. Which is going to take, that's going to swap it, right? You understand. Okay, we're going to take this one over to what? T2. And then notice where this guy goes over. It goes over to what? T1. Now they draw them up here, but the connections are going to be down here on the motor, right? You understand that where the jumpers are? Well, no, you can jump them on the relay. Because they're labeled T1, T2, T3 on the relay too, right? But what circuit would we do? Well, the same circuit. That would be the same circuit. Just now we would buy 3-phase contactors, right? You understand that? We'd make sure our 3-phase contactors have at least one auxiliary contact on them because we need an auxiliary contact for the ceiling. And ours has this. Now, normally what we would do, since you're controlling one motor, if I go to a dual voltage three-phase motor, since it's a dual voltage motor, it means we've got to have overloads because we can't have a dual voltage motor overloads inside the motor. Y'all understand why? Why is that?
You can have dual voltage overload.
We can't have internal overloads on a dual voltage motor.
If you got fuse in there for the high voltage, you won't let the motor start for low voltage.
That's a good shot. The problem is these overload sensors sense current. Okay? These overload sensors sense a current. If I wire the motor for high voltage, it's going to pull less current. So if I have overload sensors for high current, for the low voltage, it won't trip. If I have the wrong overload sensor in there, wrong overload sensor in there, then it's either not let the motor start or it burn the motor up. So if you had the low voltage sensor and you wired it high voltage, it would burn the motor up because those guys are designed to sense a higher current, right? You understand that? Because remember, horsepower is about what? Per watt. 746 watts per horsepower. So it means if I have if I have a 5 horsepower motor and we work this out, it would pull a different current for high voltage. It'd pull less current, right, for high voltage than it does for low voltage. So that's why they're going to put those things. I can't put an internal overload because an internal overload is going to look for one current, right? Because it's where? It's internal. An external overload, I can set it for the current that I want it to do. Solid states, we got that little old turn wheel on there, we can set it, right? You understand that? And of course, if we got the heater overloads like we have, then, so normally what you would do is if you buy a reversing starter, then it would have the overloads built into it, and they would be right here. And what you would do is you would have one set of overloads for both starters because it's controlling the same motor. If you bought a reversing starter. So this is actually a reverser. Unfortunately, they didn't buy one. They didn't put one with a mechanical overload button. So now they're side by side. The ones we have on the Amco line have mechanical inlocks on it. This is what our control relay doesn't have. So most of these relays have what we call it a mechanical override. The book calls it a push to test. So these are the motor. This would be a typical motor starter. It's got both the forward and reverse side by side. Which one's forward and which one's reverse? Don't make any difference, guys. It's how you wire it, right? Okay. And then they both feed through this one overload because they both run the same motor, right? Understand? Yes or no? Make sense? These are auxiliary contacts up here. You can't see it. So this one, the auxiliary contacts mount on top of the relay. The one we got, the auxiliary contacts mount on the side of the relay. So I don't know if I can get that in there so y'all can see it or not. But this is T1, T2, T3. I'm sorry. This is L1, L2, L3. It's labeled right here. It's hard to see. And down here, I can see this. T1, T2, T3 on the bottom. So power comes in on the top, right? And then the load would be on the bottom. Oops. My goodness. Now this is an electronic overload, so what we would do for different motors is we would come up here and turn this and set our overload right here. That makes sense? Now these are push to test. So I can literally take this little black thing and push it in, and that would close the main power contacts on this one. It also closes the auxiliary contacts, but it would close the main power contacts on this relay. And if I press this one, it would do it on that one. But if I came over and did this, I just screwed up, right? You understand? Because what I just did. Short circuited. So this guy doesn't have mechanical interlocks between the two relays. We have them over on the Amatrol line. They look almost identical to this, but there's a little old box sitting in the center, so they're spaced out a little bit, and those are mechanical interlocks. So mechanical interlocks means you couldn't do what? Yeah, if you push this one in, you couldn't do what? Push that one. But these relays have that manual override on there, and those guys can get you in trouble, right? So before you push those, you need to understand what's going to happen, because things are going to move. And it's no longer under control of all your safeties, all your limit switches, and everything out there that prevents people from getting killed, right? You understand? You just lost that feature. I know I told you about the guy that got killed in the top of number 8 blast furnace. Somebody went and pushed in the button and closed and pushed the wrong hopper in, and it came up and closed on him. I didn't see it, but I heard that he was already down in 2 pieces. Now, we're going to have to wire ours a little different, because we don't have a reversing contact. All we got is these motor starters. Well, it looks like some of the markings have came off this one. Here's L1, L2, L3. For some reason, this is faded out. And down here, this is T1, T2, T3. I have a marker that's not going to do it. And then, I don't know why they did this, but this is 10. This is 9. And what's between the coil and 9? Here's your overload contact, right? You understand. This is supposed to go, 9 is supposed to go to L2, right? You understand that. Then 10 is going to go back to your control circuit. When ECI wired this up, they wired in this right here so we could use it as a sealing circuit, but we're not going to be able to do it on the reverser because we've got to put a normally closed contact in there. So don't use 2 to 3. So we have a normally closed contact right here between 5 and 6. We can use that to seal it in. And here's that normally closed contact between 7 and 8 that we can use in the other relay circuit. You understand? So the way we're going to have to wire ours up, since we don't have a true reverser, is we don't have this. What we have is we're going to have this, and the corrections in the lab book. I've got to get a reverse contact right here, so I can't. So what numbers would I use? I don't have it here. So here, this is my overload. That right there would be 9. That would be 9 on the other one. This would be 10. This is going to be 10. Follow me so far? Now I need a normally open contact. I can't use the one that's connected over here, right? You understand? Because that would bypass my interlock. So what normally closed contact, what contact would I use? Okay. So I need a normally open contact. Here's a normally open contact. Can y'all see the number? 5 and 6. So this would be 5 and 6. Or 6 and 5, whichever way you want to wire it. And then I would come over here and I need a normally closed contact. I need a normally closed contact from the other relay. Right? 8 to 7, but it's going to be 8 to 7 on this relay down here. It's still the same number. So that might be 8 to 7, and this here might be 8 to 7. And of course, you know what somebody's going to do. Huh? No, what you're gonna do is you're gonna say, well, I need it 8 to 7, and you're gonna wire it to 8 and 7 on the forward instead of 8 and 7 on the what? On the reverse. So that 8 and 7 is not on this one, it's gonna be on this one, right? You understand? And of course, it's obvious when you do that, because you press the forward button, it energizes. As soon as it energizes, it drops out. As soon as it drops out, it energizes. So anybody press the start button, it goes like that. What does that mean? You got them wired to the wrong relay. Somebody in this class is going to do it, sure. It happens every class. Because you see 8 and 9, and you're up here working in the forward circuit, and you see 8 and 9, and you're up here working on the forward circuit, and you hook it up to 8 and 7. You're working on the forward circuit, you see 8 and 7, you want to hook it up to 8 and 7 on the forward circuit. But that is not the forward circuit, that's the what? Reverse. So you got to run it from 8 and 7 over to your other relay. So we're going to have two relays side by side. In fact, what I want you to do is literally overlap them. So these nuts, these bolts that stick out are far enough so you can literally overlap these two of these screws. That way you can bolt them down with one wing nut, right? You understand? And you got them real close together. I don't want them real spread apart because it makes it harder for me to figure out if they're working. So when I come up here and check this thing, I'm going to check L2, but I'm also going to check 8. I'm going to come over here, whichever one you use. I'm going to pick 7 and make sure it goes over to the other relay. Right? I understand that. But what's the mistake somebody here is going to make? They're going to look at the same relay. I'll come up here and check L2, and I didn't put my dot right there. I come over and check L2. I say, okay, you can put power on it, you go over there and you press forward, and that relay goes chatters. You can understand why, right? As soon as you hit it, F picks up. As soon as F picks up, F drops the relay out. As soon as it drops out, it just sits there. Everybody's going to turn around and look at you. And everybody needs to laugh, right? And we don't have these either. The only interlocks that we've got, guys, are these electrical interlocks. So they are going to have to be right. So this guy belongs to that relay, and this guy belongs to that relay. The overloads you don't have to wire. This is internal. This is internal. So that wire right there, you don't have to wire. And of course, this is going to be 5 and 6, and this is where you get into problems. This is going to be 5 and 6, right? You understand? So you need 2 start buttons. So odds are you need 2 start buttons. So you're going to, for this one, you're going to use that 3-button push button panel, right? Because you got everything in there you need. You got 1 stop button, which is all we need. And then you got what? Now, can this be plugged? Sure, it can be plugged. So this is one of those situations right here. I could hit that stop button, and I could flap over here real fast and hit the reverse, right? You understand? So who's it up to on this circuit not to plug the motor? It's up to the guy operator. It's up to the operator. So you hit the stop button, then you do what? Wait on the motor to coast down, and it'll take a little while on ours. We don't have a load out there. And then what do you do? Then you can hit the other button. Are we okay? So there's going to be a few notes on this lab if I can find it. No, don't want that one, Rich. So this is, I think, CR1. I think it's CR1. So what you're gonna do is whichever lab you're working on, I want you to go and do, once you finish the lab you're working on, I want you to go and do MOC2. And then after you do that, just to play around with the motor a little bit, I want you to go up to CR1. Is it CR1?
In the lab,
Yeah.
CR1? Yeah, CR1.
So once you wire your motor up, for low voltage, just leave it wired that way. Just remove L1, L2, and L3. So I want L1 and L2 and L3 to be put on there last, right? You understand? And just leave it wired up for low voltage. So that means later on when you come back and do some of these motor labs, you can do what? All you have to do is just bring the L1, L2, and L3 back down. This is the wiring diagram. Normally we don't use the wiring diagram to wire the control circuit. Look how complicated this thing starts to get. What we normally use the wiring diagram for is to wire the power circuit. Here's the power circuit right here. It shows I bring L1, L2, and L3. And what do? This goes to my transformer. And I also just jump them where? To the top of the other relay, right? And then we bring the bottom of the relay here. We bring the bottom of this into the top of our and then we hook our motor up down here, T1, T2, T3. Your motor's already wired up for low voltage, right? Any questions on that? So this is the only time we use the wiring diagram is on how to wire the motor circuit. Y'all see it? Yes or no? Kind of. Let me get a different color besides the one that they're using. So here's L1, L2, L3 coming out of our disconnect, which they didn't show. We should already have this over here wired up going over to our what? To our transformer, right? Which they don't have jumped, right? Okay, our dual voltage transformer. And some of y'all are using L1. Then I'm going to take L1 right here, right? This comes down to my L1 contact on my motor starter. This comes down to my L2 terminal, on my motor starter. This comes down to my L3 terminal on my motor starter. Then I'm going to take L2 and I'm going to come over here. Oh, they put their disconnect there. Then I'm going to come down to L1 on the other motor starter. Then I'm going to jump over to what? L2 of the second motor starter. And then I'm going to jump L3 over to L3 on the motor starter. So these are just going to be jumpers. Watch out for the no more than two terminals, right? Are we okay? Any questions? And then of course what will we do then? Then we'll take the bottom of our motor starter. And we don't have to do this. We're on this side over here, right? We'll run this down to T1 on our terminal block on our motor, T2, T3. So what I recommend is you wire either forward or reverse, whichever one you decide to be, right? You understand that? So we don't call these a forward and reverse circuit. We call these reversing circuits. Why? Well, forward and reverse is a relative term. I mean, it's how the motor's hooked up. How does it go through a gearbox? You know, every time you go through two gears, they reverse each other because when this is pushing down, right? Y'all understand? So when you go through gears, they reverse each other. So what's forward and reverse? You know, I can get on an elevator and there's no forward and reverse there anyway. What is it? Up and down. So what's up and down? So it's, that electrician better hook the buttons up right, or better hook the motor up right? It'd be awful you come up and hit the up button. It does what? Yeah. Of course, we don't have up buttons. All we got is floor numbers. But it would get very confused. So I'm sure they label those really, really, really well. So the only thing we're going to use the wiring diagram for is to hook up the power circuit. And here we're going to really, first time we get into the individual circuit. So most control systems consist of a control section, which we usually make that low voltage. And then the power section is usually going to be high voltage. What advantage does low voltage have over high voltage? Safer for us, right? What advantage does high voltage have over low voltage? Less current to produce that power, right? Less current means I can have smaller contacts on my relays. It means I can use smaller wire to get it out there. But it costs you the same thing to run a 5 horsepower motor, right? So a 5 horsepower motor is a 5 horsepower motor. Whether you run it on 120 volts or whether you run it on 240 volts, it's going to cost you the same to run a 5 horsepower motor. But where it saves you money is trying to connect the dang thing up, right? Makes sense. So what's the plan? So everybody in here is working on a lab, right? Okay. So what we're going to do, once you get through with this one, everybody okay there? Any problem here? Oh, by the way, one of the things that you're going to do is you're going to single phase the motor. So over here we either got 3-phase or we got single phase. There's no such thing as 2-phase. If you lose one of your power lines on a 3-phase system, you get single phase because the other one acts like a return. Y'all understand that? So we don't have 2-phase. So what would happen if I had a 3-phase motor and one of these guys right here opened up while the motor was running? We refer to this as single phase. It's a 5 horsepower motor, guys. That sucker is going to try to develop 5 horsepower. So what's going to happen is the other 2 phases are going to pull a lot of current. The motor's going to hum at you a lot. So we'll try to get a clamp on that meter when y'all do this. So we're going to deliberately single phase this. You're going to try to measure your voltage on that. 3-phase is kind of weird. So what would you think if this phase right here opens and I came over here and measured these phases with a voltmeter? And this phase right here is open. What would you expect it to measure? Between T1 and T3. T3 is open. So T1 and T2 is going to measure fine, right? You understand? T1, if I go from T1 to T3 or from T2 to T3, what would y'all expect to measure? Measure that. You got, I don't know if you, why? Well, it's not going to be half. But why? Maybe more than that? Yeah. Huh? Well, if normally on single phase, okay. So I'm just going to do this high voltage. It'll be a lot easier to do that. So normally, if we have an open circuit, right, you understand that, then we would lose it completely. Okay. But what we have is I'm coming over here and I'm putting a meter on here. Does your meter have resistance? Okay, so your meter's a load. Most meters have like 10 mega ohm resistance. So what happens is I'm coming over here and I've lost this phase right there. Well, as soon as I come over and connect here, if I connect here to here, I still have a connection between this phase and that phase right there. And my meter's only 10 mega ohms, so those coils are not going to drop hard. It's going to be a little lower, but there's still going to be a voltage there. It's going to be pretty substantial, probably over 200 volts. But you can't get any work out of it because there's no current available from that phase. What you're doing is measuring through the other phases that still have voltage on it, right? And you're taking a meter and you're hooking a load up to a path. And the meter's got such high resistance, it's not going to load it down. So three phase running 3-phase motors, it's pretty hard to find an open lead. So what you got to do is you got to depend on what most people do is they go to clamp on ammeters. So what they would do is they would clamp across the 3 phases, and one of the phases is going to be conducting 0 current. But what's going to happen is your motor's going to start humming at you because the other 2 phases are going to try to make up the work, right? You understand? So a 5 horsepower motor, by George, is going to do everything it possibly can to develop what? 5 horsepower. So what's going to happen if you lose current flow in one of your phases inside that motor, the other 2 phases are going to try to make up for it. And so what I want you to do when you do this, I want you to have your meter ready and measure this. If you're not on there long enough, then what's going to happen is you're going to kick the overload on the motor. But I don't want to run the motor that hot for any time at all. So this is going to take 2 people, right? You understand, to do this. And I think this is going to be with the manual motor starter. Oh, I didn't do that. Isn't there a manual motor starter? Isn't there a manual motor starter lab? That's the one you'll do it on. So, yeah, not a magnetic, manual motor starter. Huh? Yeah, manual control. Well, that's the one that you're gonna open it up on, or you're gonna open it up on the manual control. And what's nice about the manual controller is you got that stop button on there. So you can leave power on there for a while. Huh? Yeah. When I was in the hospital, there was a lady looking around with red beard, dead mirror. And after a while, you understand why. You guys go ahead and take a break. So this is the connection for our manual motor starter right here. It's very MAC1. So this guy right here, it don't take hardly any time to so I might recommend before you go to the reverser is do the motor, do the manual starter, and then do the reverser. Because this doesn't take long at all. It's very easy to hook up. So we have our disconnect, right? This is our disconnect at the top. We come out and we go through the L1, L2, L3 on the motor starter. All this is inside. You come out of T1, T2, T3 and hook it up to T1, T2, T3 on the 3-phase motor. Very simple, right? Everybody okay? Now here's the motor starter itself. L1, L2, L3 at the top. Here's the overloads. So everything is built inside. So here's the heaters for the overload. T1, T2, T3 on the bottom. Of course, this thing is spring loaded, so you can hear it snap. So if you hit start and you have an overload, it'll automatically kick it out with this guy, right? That makes sense? Okay. Very straightforward. Now, where we do get into a little problem is over on page MC6. So you're going to have the motor running, you're going to measure L1, L2, L3 like you've done on your transformer layout. Is that okay? That makes sense? Yes or no? Then we get down to step 4. It says press the stop button. The motor will stop. And then what does it say? It says simulate a fault in the starter by removing one of the heaters. We're not going to do that, guys. These things, screws and everything, will get all stripped out. So all we're going to do is we're going to disconnect one, and this correction's in the book when y'all look at it. What we're going to do is we're going to disconnect one of our lines going down on this side, huh?
You said MAC1? Experiment 1?
Yeah, I'm looking at page 6. Sorry. Page 6. MAC1, page 6. But the page number is called MAC6. I'm sorry I got y'all confused. And we're looking at step 4, where it says what?
First stop.
Okay, then what did step 5 say? We're not going to remove a heater, right? What we're going to do is we're going to remove one. We're not going to leave it hanging, guys. We're going to remove the wire, because if you leave it hanging, there's going to be voltage at the end of that wire, right? You understand? And then it might if the motor's running, it's going to regenerate it. Okay? We're going to move a wire. Yeah, it's up to you which one you're going to move. I think I said remove one of the lines from T2 of the motor and T2 of the motor starter. Remove the wire from bottom of the starter and the motor. It's in red over here. Then it says, do not make a mistake of thinking there will be no voltage at terminal 1. They say terminal 1. Let me change that so that'll make sense. So we're going to remove it from terminal 1. Do not make a mistake that there's no voltage. The regenerated voltage of the motor will appear on terminal 1. And we were talking about that, right? It feeds back through the motor, right? Everybody understand that? But it's going to be a little lower. It says, with the power off, connect the voltmeter to L1 and L2. And then I've got one between 6 and 7 that says, have the instructor apply power. And then in step 3, it says, what does it say? In this step, you will turn on the starter only long enough to read the regenerated voltage of the motor. Since the motor will be single phasing, the motor may not start. You may have to do what? Give the shaft of the motor a turn, because we don't have a start winding in this thing. So we have to have a phase shift, right? You understand? So what we did is we just started single phasing the motor without a start winding. And it's just going to sit there and hum. So you might have to do what? Just spin the shaft a little bit. If you don't, it's going to kick your overload out. Press the start button and read the voltage. Press the stop button real fast. If something happens and you can't get it fast enough, just hit the stop button. You don't have to kill the, you're working on a powered up circuit. You've got everything done. I've checked it off, right? You understand. Hit the stop button. Don't hit your e-stop unless something you need an e-stop, right? And then get yourself oriented, get right, and then hit the what? Hit the start button again. If you can't get it done fast enough, do what? Hit the stop button. And we're going to measure between all phases. So I've got L1 to L2 and L2 to L3. I've got a little note here that don't forget this measurement. And then you'll disconnect all circuitry once I check your work. So we're going to deliberately single phase the motor so you can see what that happens. And this has happened before, you know. We had I forgot what is that. One of these warehouses down here. One of our guys worked on it, and they had one of the motors wouldn't start. It kept kicking overloads and stuff like that. And guess what they did? They changed the variable speed drive out of that thing. You know how much variable speed drives cost? A lot. Guess what was wrong? One of the motor connections that came loose. It would. So yeah, that would. And they never even got out of voltmeter, by the way. Nobody even pulled the voltmeter out. They just thought, well, that must be wrong, and they changed it out. Not even making one voltage. You gotta be real careful around motors, guys, because these guys, especially in heavy industry, these guys are gonna have a lot of voltage out there. So make sure you follow all the procedures that your plant sets up for getting into these high voltage motors, because some of these motors are big, which means they're going to be running at pretty high voltage, right? Y'all understand that? So that's so any questions on that? So what I probably recommend you do, because these labs can be done pretty fast, right? Is to do what? Do the motor connection, then do the manual motor starter, and then go to then do the reversing. Any questions? Are we okay? Sure. So let's look back over to the reversing chapter real fast and see if there's anything we need to look at before we go loud.
The reverse of that is that's the one.
CR1, yeah. That's the one we have to keep. That's the only one I keep. That's part of our accreditation. That's our SLO. We got to keep it on. So for student learner outcomes, we have to keep all the information about that lab. And I have to keep all y'all's topic quizzes too. The inter-chapter quizzes. Well, that's part of our SLO too. So y'all don't get that back, and I wouldn't give those back to you anyway. This just shows you different reversing circuits, guys. The circuit itself is what? Here's the reverser for a single phase motor. They're using contacts because they're also killing the field. But we could follow this through. Anybody want to follow this through? So what should they have reversed? So single phase motor, what should they reverse? Sounds like start one. So let's come up here and let's bring in the first contact up here. So let's close the forward. So that means L1 would come in from this direction, right? L2 would come in. So this goes to our run winding. This goes to our start winding. And then this guy right over here comes in, right? Goes through our centrifugal switch, goes to the start winding, and then this is the common right here. It comes straight through, so this is never going to change. Okay. So just for, it's AC, guys, but just for seeing if it swaps, let's come up here and reverse these colors. So we'll use L for, I'm going to use red for L2, and then I'll use brown again for L1. So right now the red one came up to the top, right? So let's come up here and I'll say, so to start off, we brought L1 up here. So we'll come up here and close these contacts, and we'll take L1 through. Did I do that right? Looks like it. Go back and do it. It looks like it's going to go the same way, and I know it's got to reverse. So let's use red for L1. So L1 will go where? It would go right here. And missing something? Does it go anywhere else? Oh, I'm sorry. Yeah, it does. Right here. Still here. And goes to the start of. Are we okay? And then L2, let's use blue for L2. So L2 would come right here. Goes to the bottom of our start winding, right? And then it also comes over here. L2 comes over here and goes to the other side of our run winding. So if this is right, the run winding should stay the same. So this is blue, this is blue, and this is red, and this is red. Okay. So now what we'll do is close these guys over here. So L1 comes down to here. Okay, so what do we get down here now? Got red, right? Right. And this comes back over here, so you see we still have red here, right? Okay. Then L2. We still have blue. Now blue comes over and does what? Goes to the top, okay, where the red was, right? And of course I'm not gonna follow it. So you see we left the run winding what? Left the run winding alone. Now what circuit controls these? The same circuit that the same circuit we drew to start off with, right? That makes sense? So the control circuit for a reverser is basically the same whether you're reversing a single phase motor, whether you're reversing a DC motor, or if you're reversing a three-phase motor. We look at a three-phase motor, so what would be left, of course, would be the different series motors. I mean, this would be this would be a DC motor, and all they're doing, this is a series motor. So what we should find here is it swaps what? Should swap the armature and leave the what alone? The series cell alone. And it's basically the same way. And of course, this is a shunt motor. But notice on the series motor, the field is labeled S1 and S2. And these shunt motors are labeled what? F1 and F2. I mean, we can follow this through, guys, but it would come up and do what? So DC motors, and this is a permanent magnet motor. And of course, here we have to reverse the connection on the armature because we can't reverse it on the field without taking the motor apart and switching the magnets around, right? So we're not gonna get it. This is a drum switch reverser, and it does the same thing as not manually. So you'll see a lot of things that still use these things. Of course, the advantage of these manually controlled starters and these manually controlled reversers is you don't have to have the control circuit to manage them. It's got to center off. Why do we want to center off? Why do we want to center off between forward and reverse?
Because you don't want to go forward or reverse. There you go. Or let it slow down.
Yeah, we don't want to do what? We don't want to plug the motor. So instead of adding a real fancy circuit, we have an anti-plugging switch. It's a centrifugal switch that spins with the motor, and the motor can spin in either direction. And what it would do is it would open up the other lead, kind of like the electric seal-in. This would also add a feature to that if I can find it. We got one. Let's have one here. What you get with we got an anti-plugging switch over there somewhere. And what it does, it's got a centrifugal switch on it, and it goes in both directions. So if the motor's running, it won't let the other circuit come in. Well, that adds more cost to my circuit. So most of these people are going to depend on the operator to not do what? Not plug the motor. So to do that, then we got to have some way that we can put power to the reverse or forward. So that's why a lot of these reverse manual controllers has an off in the center where you can hit it off, right? You understand? Or you can hit it there on purpose. Let's see, reversing motors. Those other things they were looking at here too, where they have mechanical interlocks. Are we okay there? Huh? Okay there?
Remember that it's a V.
Yes, V. This would be what we're going to look. This is the ideal situation where you have both electrical interlock and mechanical interlock. We don't have a reverser for this code. So we're going to use two magnetic motor starters, right? You understand that? We're not going to have a common overload. So our motor starters don't have this, and we're not going to connect that wire right there because we don't have a common overload for both of our motors. So when you look at our book, it's going to be ours is going to be like that. But remember that contact is being controlled by that relay, and this contact is being controlled by that relay. But they're going to have exactly the same numbers because it's the same type of manufacturing, same piece of equipment, right? You understand that? This one is overload. We could do this. I think one of our labs does this. It's drawn wrong. Here we actually use interlock switches. So we have this, guys. We've got these switches over there. We've got that 3-button push button station where we can do what? We can use one switch as a normally closed, but we also have a normally open, right? You understand? So what I would do is I would put the normally closed up in the reverse, and down here I would put the normally closed right here. Now the problem is that this guy right here is hard to keep from plugging. So I don't know if anybody's going to get to this one or not. Start, stop, forward, reverse. Everybody understand how we can create a run circuit and a jog circuit on a motor? So I need to jog a motor, but I want the motor to also run. So how would I do this, guys? So right now, all I can do is run the motor. I press the start motor, the motor runs. Until I do what? Press the stop button. how would I make, say, how would I add a jogging circuit? Anybody got any ideas? No, probably not a push button. What we do, come over here and we'll put a switch right there. So I'll open up the switch. We're going to use our selector switch. I open up the switch. Now, every time I hit the run button, it's going to do what? It's going to jog, right? I close the switch. Every time I hit it, it's going to run, right? So this is and you see this used all the time. Because if I wanted to jog the motor and I had a ceiling circuit, I was constantly doing what? Trying to hit the start and hit stop, hit start, hit stop. So we have a little switch up here that says run and jog. We just flip it over to jog, and now we could do what? Yeah, we could bump it. Yeah. So that's a jogging circuit. Very simple circuit. And I think one of the labs we're going to do, if you get that far. So we got one more lecture that we're going to do, and it's going to be timers. So what you need to do now, and everybody has to do the reversing circuit. That's our SLO. But before you do the reversing circuit, I want you to do that motor circuit. And I recommend that you go ahead and do the manual circuit, because this will just be putting it up there, moving your wires over, putting them down, right? So it's going to take not long at all. And then hook up the reversing circuit. There's another circuit that we're going to use. I want everybody to do one timer circuit. But if you get through with the reversing circuit and you got a little time, then what do you probably need to do? You need to start looking at the labs and figure out which one of these circuits you can connect up the fastest. You don't have to do these circuits in order, right? But right now, if you don't want to do that testing circuit where you got to hook up all those lights and stuff and that series, and remember to do that, move on to another lab that you can do faster. All the labs count exactly the same amount. So you have some labs that are, and it all averages out, right? So you have some labs that are complicated, and you have some labs that are easy. If they all count the same amount of points, then I would get rid of all the easy labs and then come back and do that. But you got to do the reversing lab. Everybody understand that? Huh? And it surprised me last class, guys. So there was a bunch of people that had all these labs up here that said, ready to be graded, that I hadn't picked up yet. And I told y'all all the stuff y'all were doing wrong, and nobody came up here and did what? Corrected their labs. I didn't understand why, but anyway. So those are gone and those have been graded. Y'all have to work on it. So any questions on reversing? So what does this right here reverse? Does it reverse a single phase motor or a 3-phase motor, or it could reverse any of them, right? You understand that? It's just a circuit. It's how we connect the contacts, right? How we connect the contacts depending on which one of these motors that we're going to reverse. Okay. Any questions? Y'all know all the answers?
No, just
Well, then y'all need to have some questions then, right? Ask them.
It's hard to formulate a question. You just trying to take everything in at one time.
But once you get to what you're doing, then the question comes in.
Yeah, when you just hand on this when you start.
Just looking at it, the story versus putting your hand in it, and then the question come up, why is this, why is that?
And by the way, when I come back there and I check the circuit, I'm not checking to see if the circuit's right. I'm only checking what? L2. So, and if it's wrong, you just say, I need power back on. You go back, you troubleshoot it. You need power back on. I come back and do that. But if L2 guys are wired wrong, then you're going to what? And all you need to do is just make sure L2 goes where? To where it's supposed to go. Are we okay? All right.